All right, welcome to day 8 of Advent of Code. Today our problem is called Haunted Wasteland. And essentially what's happening is they give us a network of labeled nodes and some instructions. And the instructions basically tell us for each step that we take whether or not we should pick the left or the right node. And this helps us navigate through the network. And the goal is that we'll start at node AAA, and we want to end up at node ZZZ. So here it gives us an example. The first instruction is to move right. So starting at node AAA, we pick the right node, which is CCC. And then the next instruction is to move left. So we look at node CCC and we pick the left node, which is in this case ZZZ, and we're done. So it only took us 2 steps. But here in this example, so you'll start at AAA, you'll pick node B, and then you'll go to node B and pick node A again, and then you'll pick node B one more time, and then you'll be back, and then you'll be out of instructions, but you don't stop there, you only stop when you reach node Z, so you have to loop back around, and you pick A, B, and then Z, and you're done. So in this case, it was 6 steps, even though you only had 3 instructions. Okay. So the way that we're going to implement this is pretty straightforward. So let's head over into the code directory and create a new folder called day 8. We'll cd into day 8, open up part 1, and start coding. So the first thing we want is a way to store our instructions. And I think the best way to do that is to store a vector of integers, and they'll be binary integers, and we'll just call it instructions. And then so basically, if we run into, if one of the instructions says right, we will, that will correspond to the integer 1. And then if it says left, that will correspond to the integer 0. And that will give us an easy way to index a vector that we work with in the future. So again, if the character that we encounter is an R, we should push 1 to the vector of instructions. Otherwise, well, just to be explicit about it, let's say if we encounter an L, we'll push a 0. But you could just use L's there because there's only right and left. Great. And now let's set up our network. So I think the best way to represent this network is as a map. And so we're going to map from a string, which will be our source node, to a pair of, well, actually, let's use a vector, to a vector of nodes. Or yeah, to a vector of like target nodes, right? And this vector will always be of length 2 because we only have 2 target nodes, the left and the right node. And we'll just call it node map. And then we're going to iterate through the input. And so if we look at the input, we should probably get the test input. So we can always start for the node map, we can always start on line 3 because the first line will always be in the instructions and the second line will always be empty. So for int I equals 2, because the input vector, of course, is 0 indexed, I is less than input.size, I++, we want to say, let's see. So we will define our source node. I should name my variables. Okay, define our source node to be the substring of the current line, starting at index 0 and going for 3 characters. Additionally, we can define our vector of strings called destination, which will be 2 nodes. So the first one will be the substring from character 7 going for length 3, and the second one will be the substring going from character or index 12, and also of length 3. And you can check these 7 and 12, but they should be right. And then finally, in here we will set the entry, or we'll set the key source equal to the value of destination, and we will have our map. Great, and now we can actually perform, I guess, the simulation or go through the network. So what we'll do is we'll say string current node is equal to AAA because we'll always start at AAA. And then while the current node is not equal to ZZZ, we want to first figure out where we should move. And the way we're going to do that is we're going to define an integer index, and in our answer up here is where we'll store how many steps we've taken. And so we can say the index, or I guess the instruction, will be located at the index given by how many steps we've taken mod the length of the instructions because we want to wrap around. And so if, or no, we don't need the if here. We can say current node is equal, or we can reassign current node to the node. So this node map of current node will give us a vector, right? And it will be this destination vector. And then we want to take the we want to pick from here whatever the instruction tells us to. And so we'll say we'll grab either a 0 or 1 for the instructions vector based on what the index is. And then, of course, if the current node is equal to zzz, we want to stop iterating, and we want to increment, or otherwise we want to increment the answer and move on, because the answer again is how many steps we've taken. And then finally, so because we break out of here when we encounter, as soon as we encounter a zzz, we need to add 1 to our answer. I'm fairly certain that if we took this line out and just let the while loop break, we could get rid of the +1 here, but this is how I implemented it. So if we compile part 1 and run it on the test input, we do in fact get 2, which is correct for this first test input. And now let's run it on the second test input. We'll just replace it here. And oops, I closed out one too many times. We're expecting 6, which is what we get. Wonderful. And then finally, let's run it on my real input. We get 15,989, and that is correct. Great. Okay, moving on to part 2. So part 2 is pretty similar. Now you can see the node names change a little bit, and it tells us that we're interested. So rather than just doing this like one simulation where we start at one point and end at one point, we actually want to start at multiple points. So we want to start everywhere, or we want to start at every node whose last character is an A. And then we want to calculate, based on where those nodes are, how many total steps we have to take until we are only standing on nodes that end with Z. So here it gives us kind of a simulation. So you're going to start at 11A and 22A. And if we, and so we kind of move in unison. So we're going to start at 11A and move to 11B. And we're also going to start at 22A and move to 22B. And then we're going to follow this right instruction, and we're going to move right both times. So the 11B will bring us to 11Z, and 22A will bring us to, or excuse me, 22B will bring us to 22C. And so here you can see it takes us 2 steps for path 11 to get from A to Z, and for path 22 it takes us 3 steps. So we can't, so it's not like the sum of those, right? Because you want to be simultaneously on 11Z and 22Z. And so instead, it's actually the least common multiple, because after you perform 6 total steps, you're standing on 11Z and 22Z simultaneously. So it's not the sum of the distances, it's the least common multiple. But you can see here, with this many steps, you couldn't just like brute force this and wait until all of your nodes were simultaneously on Z. So what we're going to do instead is we're going to, we'll simulate it simultaneously because you need to step every node according to the same instruction. But as soon as a node is done, we're going to stop simulating it. And that will give us basically the path distances for every node, and then we can, or for every starting node, and then we can take the least common multiple. And so we don't need to change a ton about this part of our code for part 2. Let's just paste it in here. We still want our node map and our instructions. But what we do want to change is how we go about this while loop. So first of all, what I want to do is, well, if you look back at part 1, we started with a 1 current node, but now we're going to have a vector of current nodes, right? Because we have to keep track of like multiple paths, I guess you could say. So I'll define a vector called current nodes, and we're going to populate this current nodes vector by iterating through our node map. So for, let's see, we'll say for auto iterator equal to node map.cbegin. And then we want to iterate until we reach the end of the node map. And of course, we want to increment by 1. What we're going to do is we're going to say, okay, so the key value, or excuse me, the key of this iterator is going to be our source node, and then the value is going to be our vector of destination nodes. And so we're going to say if the first value of the iterator, which again is the source node, if its last character And again, because all of the nodes have names of length 3, its last character will be at index 2. So if its last character is not A, we can continue because we don't care about that node, at least right now. Otherwise, we want to push it onto our current nodes, right? Because this is like one of our starting nodes. But we don't just want to store the node's name. It'll be useful to store 3 pieces of information. The first, of course, is its name, because we need to be able to look it up in the node map. But we also want to be able to store whether or not the node is active. So basically that means, have we reached its end yet? Because this will allow us to stop iterating before. So like, for example, we can stop in the example, we're able to stop iterating at step 3 because this node would be deactivated and this node would be deactivated, or this path, I should say, would be deactivated. But if we didn't have that active field, then we'd have to iterate for 6 full steps. And clearly you can see with this answer size, that won't be possible. So what we want to do is we want to, rather than store just a string here, we want to store a vector of strings. So let me write that out. And then this last field is going to store how many steps it took us to get to the end of this particular path. Okay. And so now we can start writing our while loop. So I'm going to define a helper function that's called exists active nodes, and it will accept our current nodes vector. And so while there are active nodes, we want to perform our iteration, right? So do stuff here. But first we should write the exists active nodes. And before I forget, what I want to do is change our answer to a long value, because once again, you can see this is much larger than the C++'s limit for a default integer. And I believe that's essentially all that we need to change for now. So let's write the check or exists active nodes. So this will return a Boolean, of course. So and it will accept. Let me just grab actually this whole thing, because this is exactly the input parameter it will accept. And then what we're going to do is we're just going to iterate. So for auto node of current nodes, and we're going to check if the node is active. And so if node 1, because that's the index at which we're storing the activity of the node, will return true. But if we get to the end of the vector and no nodes are active, we'll just return false. Great. So that's pretty straightforward. Wonderful. Okay, so now we can get back into our while loop here. So just like last time, we're going to want the index of our instruction, and that's no different. We still want to wrap around, so we're going to use the modulo operator. Now, what we do need to do is say, so now we're going to, rather than just like increment the one current node, we have to increment or check basically all of the current nodes. So we'll loop through the current nodes vector. Let's see, I accidentally had caps lock on there. And we'll define our current node. So std vector of, and this is a vector of strings. And I think it probably would be slightly a better practice to be using a tuple here, but I'm too lazy to change it. So let's keep using the vector. And the reason for that is because it's a fixed length. And actually, no, it would not be of best practice, because we do need to be able to mutate the values in this vector. So never mind. Definitely use the vector. And so our node will be equal to current nodes at index I. And then we want to say if node 1 is equal to, so if the node is active, right? If it's not active, we should just move on, right? Otherwise, so now we can check, now we know the node is active. So we can say if the last character of the node is equal to Z, right? So the node 0 points to the node's name, and then 2 will be its the last character, because all the names of the nodes are of length 3. We're going to set current nodes I at index I of 0 equal to node 0 dot substring 02 plus Z. So basically what this is doing is this is giving us, this is making sure that now when we encounter this again, or sorry, when we encounter like line 67 again, line 68, we will be able to like move on, right? And so now we also need to change the activity field to inactive. And then we need to change the steps, right? So I'm going to grab this, and the steps will just be equal to however many steps we've taken so far. And of course, we're storing that in our answer again. But I am going to convert it to a string because this is a vector of strings. So just like that. And then the last thing is for all nodes, regardless of like where we are, we want to change the current node at index I of 0 to the node map of the current node. And then we need to extract the whether it's left or right from the instructions, right? So basically just like this. Great, and that looks good. And then of course we need to increment our answer by 1. Wonderful. And now let's find the least common multiple. Or so first let's populate a vector of long values called step counts, and this will just return, or this will store all of the like step counts for each path. And so for vector, or for, I should just be using auto here, it's fine, but I already wrote it. So for current nodes, we want to push onto step counts, push back. We're going to convert the step count here that's currently stored as a string. We're going to use the s to ll function on node 2, or node at index 2, right? Great. And now we need to calculate, so the answer is going to be equal to the LCM of step counts. But I don't have I don't have an LCM function already defined. I should probably add one to my boilerplate code though. I feel like that would be helpful. Maybe I'll do that. But for now, let's just write it. So first we need a greatest common denominator function. So we're going to define a or a function that returns a long called GCD, and it will accept 2 numbers, A and B. And I think for at least one of these functions, you'd probably be safe to use an integer, but again, just to be extra sure, make sure you're using longs here, or at least longs, because we never know how big the input is going to be. And so what we're going to do, we'll make this a recursive function. So if b is equal to 0, we'll return a. Otherwise, we'll return the greatest common denominator. So we'll just, again, recur here and pass in the remainder when you divide a by b. Great. And then we can use the GCD function to write an LCM function that will accept a vector of long values called numbers. And what we'll do is we'll define actually a function in here called calculate LCM, which will just accept 2 numbers, so a and b, and we will return a times b divided by the GCD of a and b, right? And this is the definition of a least common multiple. And we do need a semicolon there. And then finally, we can say long result is equal to numbers at 0. So we'll just give it the default value. And then we will iterate through the numbers vector. I is less than numbers dot size. I spelled numbers wrong. Numbers dot size, I plus plus. We will say result is equal to calculate LCM of result and numbers I. And then we can just return result. So return result, and that looks good. All right, I need a semicolon. Okay, wonderful. And I'm pretty sure that should be all we need. Let me just go down here. Yeah, should be good. So I know I've been saying, or no, we don't need this. We should not, do not cast that back to an integer. Okay, so we'll compile part 2, p2 test, and we do get 6, which that is correct, but let me grab this input. There we go. So part 2 test. Okay, that's good. It is 6 steps. And then if we run it on the real input, Let's hope that it is correct. We do get this huge number, and yeah, that looks right. Okay, pretty straightforward day today. I hope everything made sense, but if it didn't, as always, please leave a comment. But I will be back tomorrow for day 9.